Welcome to this lecture on this second lecture on this module 4. In this module we are discussing on functions of random variable, and in today's lecture what we will do, we will just learn about this different method. So, if you recall that our last lecture, in that last lecture we discussed about the fundamental theorem, and in that fundamental theorem we have seen that if there are different roots of a function of random variable, then how we can make a general equation to find out the probability density of that function of the random variable. From the information which is available is this original random variable, its density is known, and the functional form with this new random variable is known. So, using these two equations we have seen that what is the fundamental relationship between the probability density function of these two random variables, and keeping that theorem in mind, today what we will do is that we will find out different methods, and these different methods are basically based on the different assumption, but so far as the fundamental concept is concerned is same what we discussed in the last class. So, what in today's class what we are discussing is that we will discuss about different methods to get the probability density of the functions of single random variable. So, to get that probability distribution, both that PDF and CDF, there are different methods are available, and as I told that all these methods are based on the same fundamental concept of the fundamental theorem that we discussed in the last class, and we will use the same concept to discuss about our different methods, which these methods are based on certain assumption which are realistic so far as application is concerned. So, the first thing is that method of distribution function, then the method of transformation, and then method of moment generating function we will discuss. The first we will discuss that method of distribution function. So, if I before I go to that theoretical thing, if I just draw here the concept of that what's the fundamental thing is that just relating the fundamental theorem of our last class, that what we have to find is that if there are two random variables, one is this x and other one is your y, and there could be some relationship of this equation, and what we are supposed to do is that we have to find out. So, we know the what is the density function for this variable x is known. So, what we have to find out is that for a particular value of y, we have to find out what is that what is the domain for that particular value x. If I am considering that probability the method of distribution function, here the method of distribution function means what we are talking about is that CDF, that cumulative distribution function. So, to now if this is a specific value of this random variable y is this small the lowercase letter y, then what I have to find out is that what is the corresponding domain of the random variable x. So, if I want to know this CDF, that means that y is less than equals to this specific value y. So, that is this side. So, this domain is the equivalent domain for this x is that specific value of that random variable x and its domain. So, the CDF, that is the probability up to that particular value y is equals to probability of the random variable x up to this specific value of this x. Now, if there are in the last class we have also seen that if in case, so here these domain are same and continuous domain from this minus infinity to this y, and for x this minus infinity to the x. Now, for some other value it may so happen that there could be some different zones. Okay. For example, if I just take the another value of this y, let us say that we give the name as this y prime, then there could be that this domain can have different domains for the random variable x. The first one, this could be this x prime, so which is less than equals to x prime, which is corresponding to this point, plus another domain which is your this one. If I just give these names as x double prime and this is x triple prime, then this zone as well as from minus infinity to x prime, summation of this probability for the random variable x should be equal to the probability of the random variable y less than equals to y prime. So, this is the concept where what we are talking about this method of distribution function. So, what we have to do is that we have to find out what is the inverse relationship, and that should be expressed in terms of this y to get that probability this cumulative density function for that new random variable y. And once we get this one, we can get that probability density function by their differentiation. So, this is the keeping this one is the basic concept. We will now see that method of distribution function. So, first what the so far as the fundamental definition is concerned, that is what we are meaning is that what how these two variables are related, that we have discussed. Then the distribution function of the discrete random variable as well as this distribution function of the continuous random variable, there will be a little bit little difference between these two when we are talking about the discrete as well as this continuous. We will discuss this one and we will see it through some example. Basically, what we will be doing, we will be using the same example that we have used in the last class, and we will show that in the last class from the fundamental theorem we have solved that equation. Now, with the help of this method of distribution also we will solve the same problem to show that how what the result comes. Just to differentiate what is this difference is there, if any, what is the difference. So, we will use the same problem that we discuss. So, what we just now is discuss is that the distribution function, that is the cumulative distribution function f y of a random variable, is the probability of the event that this y less than equals to a specific value y consisting of all outcomes xi, such that y xi is equals to g x xi, which is less than equals to y. So, that means here what we are trying to say, this is the fundamental thing of this cumulative density cumulative distribution function that we discussed earlier, is that. So, if I want to know this f y, then I have to find out the region, I have to find out the probability that this is less than equals to y. Now, referring to the figure that just now I drawn, is that what we are going to get that for this f y y is that this f y y is nothing but the probability of the random variable less than equals to a particular value y. So, this is from the fundamental this is from the basic definition of this cumulative distribution function that we discussed in the long back earlier classes. So, some specific value y is there, I have to find out this probability. What is known to us, the properties of this x is known. So, that is why I have to relate it to this random variable which is known to us, which is x here. So, thus if I now want to know this f y, which is equals to the probability of y less than the specific value y, which will be equal to, now I am relating it to that functional form, the functional dependence between x and y, that is y is equals to g x. So, I am replacing that one. So, this g x should be less than equals to y. So, I have to find out some domain in the x which corresponds to that for the random variable y, which is less than the specific value of y. So, it follows that probability of y less than equals to y is equals to x less than equals to g inverse of y, directly from this equation. So, this g inverse y is the another function which I am just taking the inverse function of this gx, that functional form is there. So, what is here is that I have to express that functional dependence in terms of y. So, if I know this one, now probability of x less than equal to a specific value, we can easily get it from that the properties of this random variable x, which is, we know that this cumulative distribution is fx for that specific value J inverse y. Now, this distribution function is, you know that this is a cumulative distribution function, and once I get this cumulative distribution function, then we can differentiate it to get that probability density function. So, in brief, the distribution function technique, that is cumulative distribution function technique, is that to find the value of x such that the gx is less than equals to y form a set on the x axis and which is denoted by ry. So, here if we refer again that for any specific value for this y, for a specific value of this random variable y, I have to first identify the what is the set of x that corresponds to that specific value of y. So, this one, for this here this y prime, that set is nothing but, one is that from minus infinity to x prime and x double prime to x prime. So, this is the full set of the x that I have which is corresponds to that minus infinity to y prime. So, this is that set which we are talking about, that ry, that is the corresponding set for this specific value of the y. This is what is explained here. So, first of all, this for this in this technique, the distribution function technique, we have to find the value of x such that this gx is less than y, form a set on the x axis, and this is denoted by ry. Now, the probability that gx less than equals to the specific value y is obtained, that is the probability of gx less than equals to y by integrating the density function of fx. So, integrating this density function of fx, so this fx x is your probability density function of x. Now, if I integrate it, we will get that probability that cumulative distribution function, that is CDF of x, and from that CDF of x we will get that what is that distribution of x for a specific value, that this probability will be obtained, which we discuss in this slide. That is, if I know that specific value of this y, and if I know the probability that cumulative distribution function of x, then from this form we can get that probability, that is probability of this specific less than specific value of y is equals to from that cumulative distribution function of x. Now, once we get this y is obtained, then we know that this density, that is PDF, probability density function, can be identified, can be found out by the differentiation with respect to y. So, we know this one from this basic principle of this CDF and PDF. Now, so we will just see the two different thing for this discrete random variable and for this continuous random variable. There is a slight difference in the sense, maybe when we are talking about this equational form, that difference may not be may not be easily understood, but in the next method when we are going to talk, that is method of transformation, that time it will be more clear. So, but here what we are trying to say, just we will just differentiate from in terms of integration or in terms of summation, what the case may be. So, maybe that integration is for the continuous random variable and the summation for this discrete random variable, because we know that for the discrete random variable the probabilities are concentrated at a particular value. So, we have to sum them up. So, here, so that is why it says that for the discrete random variable x, that f y, when we are getting that another function, is equals to the summation of the probabilities of this xi for all such xi which is less than that g inverse y. The g inverse y means that inverse function of that functional relationship between x and y. So, we have to first identify that which are that specific values of the x which is less than this g inverse y, and for those specific values whatever the probabilities are there for the x should be summed up, and that should be equal to the probability of that specific value of this y. Now, for the continuous one, continuous random variable, we know that if we have this probability density function f x of x, then to find out this f y of y, it should be integrated for the set for which this x is less than equals to g inverse y. So, you know that. So, this set, this form just now we discussed in this pictorial form, that this is your basically that R y, that set for which this condition is satisfied. So, if we integrate over this region, then we will get, so other words from this leftmost support, that is from the minus infinity to that inverse, we will get this this form, and this will be equal to the probability of y up to the specific value small y. So, here means even though this is shown in a very compact form, it may not be, depending on this how many roots are available here. For example, here that we have shown in this figure, that for this one the integration must be the summation of this. So, minus infinity to the x prime. So, the integration from this minus infinity to x prime, that f x of this x dx, plus I have to take another integration, that is from the x double prime to x triple prime, that is this zone f x dx. So, if we get this form, then this will corresponds to that f y of that value f y prime here, this f y prime we will get. But if I just want to take that this point, that is f y of y, this is simple, you can get that from this minus infinity to y f x x dx. So, this will be equal to this probabilities. So, now we will just show this is not very not specific to any particular civil engineering problem, but this is very important to understand the concept that we discussed so far. And this is taken from the Papulis book, Papulis and Pillai book. So, here what is shown here is that a relationship between this x and y, this g x is equals to y, you know that this is the functional form. So, this is, if this is the type of relationship, then we will see what how it happens, because whenever we are talking about, we are just giving some values to this g x corresponding to a specific value of y. Then here in this form you can see we have taken this example just to demonstrate that if these things becomes flat, this functional relationship becomes flat at some point, then what will happen? This flat at some point means mathematically I can say that the rate of change of y, that is g x, the rate of change of y with respect to rate of with respect to x, it is constant. So, so it becomes, when it becomes flat, then how this this distribution looks like that, that we will see. So here what we have to do basically is that we have to first of all find out the three different region of this function. So in such cases, so where there you can see that there are three distinct different dependence for over these three different zones. There is one is that with respect to x, if I see that one, the first zone is that less than equals to minus b, second zone is from this minus b to plus b, and the third zone is from the b from the greater than equal to b. So for the first region, that is when the x is less than equals to minus b, then the value of this gx or the y is minus b, and for this region, that is when this x is greater than equal to b, the value of y is b. This will not be minus b, this is b. So value is value of y is b, and for the zone from the minus b to plus b, it is varying linearly. Now in this case, how, if we know the distribution of this x, what should be the distribution of gy? So for this region, it is whatever we have discussed so far is easy to get, because I will just get any specific value of this gx, that is of this y, find out what is the corresponding value of this value for this x, and find out their density function. So that is easy, but here we are more interested to know that how it is for this this zone where this relationship becomes relationship is constant. So these two zone we will see. So this figure, what it is showing is that how this fx of x looks like, and a function is taken, so that function, the pictorial view of that function is looks like this. Obviously it starts from 0. You know that it is CDF, cumulative distribution function, and it is shown that it is asymptotic to 1 at infinity. Now, so what we have to first, as I told, that we have to find out that three different regions. One is that with this y equals to gx, that is with respect to this figure that we have shown just now. It follows that this y is discontinuous for two cases. One is that for this at this minus b, means less than minus b, and at another point which is equals to b. So at this point, this function is discontinuous, because you know that mathematically two straight line is meeting that point. So according to the method of distribution, the first, if this is a general form, as I just explaining for the continuous random variable, that y is equals to the probability of y less than equals to a specific value of y. So and this y is replaced by its functional form gxy. Now keeping this one as this basic equation, now there are three situations can happen. The first is that y is greater than b. If y is greater than b, then for the gx less than equals to y, that is specific value of the random variable y, for every x, y is equals to 1, because that is the maximum value that it can take. So at so for this greater than equal to b, this fy is 1. Similarly, if I just take that y less than equals to b, then for this gx less than equals to y for no x. So that is why this cumulative distribution function, the value of the cumulative distribution function for this zone, that is y is less than b, is equals to 0. Now for this b, that is from the minus b to plus b, if I come to this region, then by the nature of this functional dependence, you can see this is just a one specific value you will get for the x for a specific value of y. So any value you take for this gx, that is for this y, from this minus b to this plus b, then it will correspond to a specific value of x. So, less than equals to that value of y will be equal to the less than equals to x of that corresponding value on this x axis, means that for the random variable x. So, for this minus b to plus b, that distribution of this y will be same as this value for this fx, and for this when it is becoming greater than b, it should be equal to 1, and when it is becoming less than minus b, it should be equals to 0. So, what now if you see it here pictorially, then from this, from the minus infinity to minus b, the value of this fy is 0. Then at this value, that at minus b, this fy is becoming is equal to the value of that fxx at minus b, and it is going on following the same curve up to the point b, and at point b this is equals to value 1. Now, if you recall our description of this CDF, means few more the earlier classes we discussed. So, this straight line basically is an indicative line. If I just draw it here, then you recall that the staircase function that we drawn while describing that that CDF for this discrete random variable, then it looks like this. So, what happens now? I am using another ink. So, if this point is your minus b and this point is your plus b, then the CDF comes up to here, then this is just an indicative line, because at b this is equal to that particular value of this y. So, it follows from here and goes up to this plus b, and then this becomes equals to 1, this is 0. Now, the way the function is defined here, I will just come back to this figure once again, refer to this slide now, that way this function is defined here, that is that gx is constant for x less than equals to b and x greater than equal to b. So, the constant form is from this equals to b. So, when we are taking this this form equal to the similar form of this fxx for this region from this minus b to plus b, that means this b, that constant value is included for the value up to minus b. So, what I can showing here is that, so at minus b this value is 0 and at plus b the value is 1. So, this line, which is the similar form of this fx, cannot take this value. So, I am just, if I just zoom this part, is it looks like this. So, it can go as close as plus b, but it cannot take the value plus b. Just recall our description of this CDF for this for the throwing a dice in few previous class we discussed. So, it can go and we cannot touch that b, because at b the value is 1. Similarly, for this minus b, there will be another, it cannot touch this minus b. So, it comes like this, because at minus b the value is 0. So, this one I think making this thing clear. So, what we are trying to drive is what we are trying to convey here is that when this function, the rate of change of that y, become constant with respect to x, at that point we can observe a discontinuity in the cumulative distribution function of y, which is shown in this specific example. To illustrate the theory that we explain now, we will take a similar problem. Similar means that we took in this in the last class also, and we will see that how we can solve that particular thing in this context. Here we will take that problem. There are two variables. One is that this z, which is basically that your wave height when there is a wind is blowing on the free water surface, that wave height depends on various factors, and also it is related to the square of the wind velocity. And so these two are related like this, and obviously there will be some constant will be here that we can see. Say that this constant is some a. Now here the question is that this v, if we know the distribution of this v, whether we can get the distribution of this z. Now this wind velocity, generally what we see that this is having a distribution of this wind velocity is an exponential distribution. Say that this is looks like, you know, that exponential distribution like this, and here the support of this one is greater than equal to 0. In the last class, the problem that we took, this one is having a support over this minus infinity to the plus infinity. There we are talking about some strain energy and force, which was a standard normal distribution. So that is having the entire support of this real axis minus infinity to plus infinity, but here it is the wind velocity, so this can take only the positive values with respect to, as when we are talking about that wave height. So it is towards the obstacle where we are measuring the wave height, and this is the distribution and is 0 elsewhere. So if we know now, here also we can get that similar to this earlier the last class problem, that is this v is equals to plus minus square root of z by a we will get, and obviously this minus root, the negative root is not a valid case, and that modulus of this dv dz will be equals to 1 by 2 square root a z. Now this f z of this one, the distribution of this new random variable z is equals to that this distribution of this known variable at those roots, that is z by a. If we want to write the complete expression, f v minus square root z by a, which is 1 by 2 square root of a z, which is the value of this one. Now this is basically, this is not valid, so we have to take only this value, and what we can write that 1 by 2 square root a z f v square root z by a, and this we can express as 1 by 2 v naught square root a z exponential minus 1 by v naught square root z by a, where again that z should be greater than equal to 0, which is the support of this distribution. So here we have seen that even though they are having other roots, we should not consider those roots which is the outside of the support of this random variable v. So the distribution of this z is 1 by 2 v naught square root a z exponential minus 1 by v naught square root z by a. Here the support is that z is greater than equal to 0. Discuss about the another method, that is called method of transformation, and this method of transformation is popular in the sense that in most of the engineering application problem and most of the practical application problems as well, we have seen that whenever some function of a random variable is taken, in many cases the correspondence is always 1 to 1. So what is mean by this 1 to 1 correspondence means that for a specific value of the original random variable, here we are using the notation as the x, So there will be only one value of the value of this dependent random variable, that is here we are using y. So for a specific value of x, there is only one and only one value of y, and vice versa. So this kind of transformation is called that one-to-one transformation. So if this is the one-to-one transformation, then using that fundamental theorem, that what we discussed in this last class, that can be reduced to a very effective equation, and that equation can be directly used to find out what is the probability density function directly by using that equation. So that is what our second method we are going to talk, that method of transformation. And obviously we have to remember that method of transformation means what we are referring here now is the one-to-one transformation. So here that this case 1 is the one-to-one transformation, and we will just show one example of this discrete and another example on this continuous. And there could be the another case that the transformation is not one-to-one. So we are talking about this when the transformation is one-to-one. So suppose that we know the density function of x. Also suppose that the function that y is equals to gx, sorry, there will be one g, that is the functional form, that y equals to gx is differentiable and monotonic for the values within its range for which the density fx is not equal to 0. So this is basically what we are referring is that to the one-to-one. So we will just discuss about this monotonic. What this monotonic is talking about is that if the function either is increasing, either if it is increase, so it should increase over the range of this fx, or if it is decreasing, it is decreasing. Now this monotonic means it can never if it is an increasing function, in this it can never decrease if the x1 so fine. So if this is the value x1 and if this is the value x2, and if this x1 is less than x2, then this value, that is this is your that gx1, and if this is your gx2, then gx1 always should be less than equals to gx2. If I just put this sign that less than equals to gx2, that means I am including this sign the equal to, that means it can even be flat, that is called the monotonically increasing. But if I exclude this in equal to sign, that is known as the strictly monotonically increasing. So strictly monotonically increasing means it can even not be equal, it will always increase for some higher values of the x. Otherwise, if the equal to is included, that is known as that monotonic. So this function is monotonic, that means that this transformation is always one-to-one. Now recall that we for the general discussion when we are talking about this kind of equation, so there is the possibility of having more than one roots is only can happen only in case of when this function can increase and then again decrease and then again can increase. So in this kind of situation only there it is possible to have more than one roots. So what we discuss in this fundamental theorem. So here what we are talking about, it can never increase, that is it is monotonic, that means there is always one-to-one relationship of that from this x to that gx. This is what is explained here. So so once again I read that suppose we know the density function of x, also suppose that the function y equals to gx is differentiable and monotonic for the values within its range for which the density fx is not equal to 0. So monotonic, we have explained why the requirement of this monotonic and what is monotonic, and there is another requirement is the differentiable. So, we will just see if it is not differentiable at a particular point, what will happen, and it will be clear when we are referring to that fundamental theorem. When the equation, that is g equals to the y equals to gx can be solved for x as a function of y, this transformation, that is the inverse mapping, is then used to find the density function of this y. Similarly, we can do the same when there is more than one variable x, and then that case there is more than one mapping. So, this one basically will be discussed when we will be discussing that multiple random variables. Here we are discussing in this lecture the single random variable. So, we will deal only from one random variable to another random variable, that is from x to y. So, in order to apply the transformation, there should be the one-to-one correspondence between the x and y, that is what we should discuss. Here is one example, that y equals to 1 plus 9x. So, if I take this example, then you can see that for a specific value of y, only one value of y is there, and vice versa. So, this is an example of the one-to-one transformation. Now, y is equals to sin x is not an one-to-one transformation, since more than one value of x will give the same value of same values of y. So, you can see that. So, if this is that, if so, if the function is valid for this 0 to pi, then you know that for a specific value, for the same value of this y, there are two values, this is x1 and this is x2. So, two values of this x is possible. So, that is why this is not a one-to-one transformation. Now, for the discrete variable, let the random variable x with the PMF px of x be transformed such that y is equals to gx, and the inverse function of y can be written as this x equals to g inverse y. If I just give a new function of the hy, so hy is equals to this g inverse y corresponding to y equals to gx, then this PMF of this y, that is Py is given by this Py is equals to that Px hy, where this hy denotes the inverse function such as that x equals to hy if y is equals to gx, that is the this hy is nothing but that g inverse of y. Okay. So, with this, one example we can talk about for this discrete random variable, just we will see that one-to-one transformation. Obviously, we are talking again here the one-to-one transformation, that is if the transformation have only one specific value. So, this probability of overtopping a guide band after x years from now can be modeled as a geometric distribution. Now, we discussed in previous lectures that what is geometric distribution, and in this geometric distribution the random variable that x that we are talking about, this is either the probability of success or maybe the success and failure, you know that we just generally attribute is arbitrarily. So, here that overtopping of the guide band is one event. So, that event is has taken place or not, that is if I say the success. Means we should not, socially we should not say that this overtopping a guide band is a success, but it is just mathematically whether the event has taken place or not, that is that the guide band is overtopped or not. So, that one that can happen in after x years, that means, so from this point onwards, what is the probability that the event will occur after 1 year, what is the probability that event will occur after 2 years, similarly what is the probability that it will occur after n years. So, this random variable is modeled as this geometric distribution that we discussed earlier. So, here is this geometric distribution form, that is Px of x is equals to your pi 1 minus pi power x minus 1. For this x is a discrete value here 1, 2, 3. So, whatever the year that we will take, and this pi, you know, is the probability of success, in the sense that that pi between 0 and 1, and the probability of the overtopping in a particular year. Now, the situation is this, that to make the guide band more effective, it is strengthened in such a way that if I now transform that, if I want to know that, want to do some new analysis, then the transformation y equals to 2x can be suitable transformation. Okay. Now, if this is assessed, then if I want to get some probability for this, want to know the nature of this y, then obviously I have to refer to the probability distribution for this new random variable y. So, I have to know what is the distribution of this y. So, following the same principle, that is, first of all I have to find out what is the inverse function, because you know that this I have to explain in terms of this original random variable. So, this is your x is equals to y by 2, because y is equals to 2x, that we discussed. So, thus the PDF for the y, that is probability of y, is equals to that function expressed in terms of that inverse function of that y, that is g inverse y, which is y by 2. So, this one we have just put, and we have to show that what is the possible value that y can take. So, this is valid for that y equals to, this is a mistake, that this should not be x, now this is y, the y is equals to 2, 4, 6 this onwards, because you know that y is equals to twice of the x. Now, if we just compare that earlier distributional form and this present distribution form, that earlier it was p x equals to, that is sorry, this is pi, this pi multiplied by 1 minus pi power x minus 1, and this new one is that p y equals to pi 1 minus pi power y by 2 minus 1. So, this probability of failures under the old scheme x after 1 year, 2 years, 3 years and 4 years, for example, is equivalent to the probability of failure after 2 years, 4 years, 6 years and 8 years respectively, and in this way it can go. So, even though this is a very straightforward application that what we have shown here, for this is for this discrete random variable, but if we but the concept is here is also same. So, when we are talking about the one-to-one transformation, we are finding out the respective domain for the new random variable and finding out their probabilities. Now, we will discuss about for the continuous random variable. Now, this continuous random variable, if I just want to explain first mechanically, then firstly the transformation from the PDF of x to that of y involves the substitution of the inverse function of y solved for x, that is x equals to g inverse y. So, this we have to substitute in terms of the x g inverse y. What exactly we did for this just now, that for the discrete random variable example. So, secondly, the PDF of x so defined should be multiplied by the absolute value of the first derivative of the inverse function, say that hy. So, this first derivative is called the Jacobian of the transformation and it is denoted by j. So, the absolute value of this Jacobian should be multiplied with that PDF of this y expressed in terms of this what is shown as the y is that x equals to g inverse y, that is to be multiplied. So, mechanically what these two steps says is that first of all you express the same that PDF in terms of this the new random variable and multiply it by a Jacobian. Jacobian is nothing but the first derivative of that first derivative of the inverse function of hy, that is g inverse y. Okay. Now, the same thing if I want to represent with reference to the fundamental theorem that we discussed in the last class, that we will see, then it will be more clear to us. Just recall that the fundamental theorem that we discussed in the last class, that is f x x is known and y equals to g x. To determine this f y, a specific value of y equals to g x is solved. Now, if there are n roots, that is for this equation, if there are n roots x1, x2, xn, then we have seen and we have proven that this equation holds. And we have also referred to this population pili where this proof is available as well. So, now this g prime x is also, we have defined that this is the derivative, that is the first derivative of this gx. Now, here what we are doing, what we are saying is that this is a one-to-one transformation, that means this root will always be one root. So, when we are taking a specific value of y, then there will be one and only one value of this x, because we have started with the assumption that this is the one-to-one transformation. So, there will be only one. So, straightforward what we can say is that we can just reduce these other components. This is the first, this one is the valid thing what is explained here. So, this fy y is equals to this fx x1 divided by g prime x1. Now, this gx, we know that this is a derivative, gx is equals to your y. So, now if I just, this can also be expressed in terms of this fy y is equals to dx dy, y is your gx, there is just I am multiplying, that is why I am just taking it as inverse. So, multiplied by fx x1, as there is only one root, just to make it that, so there is no x2, x3, x4, so just we are replacing it by in terms of this x. Now, what we have to do is that, because this is the fy, so you have to explain this full function should be with respect to the y. So, this should be expressed in terms of this y. Now, what is this? So, this is the PDF of this x, which is expressed in terms of this y multiplied by this factor, which is that first derivative of the inverse function, because this we have taken that inverse, the dx dy, this is nothing but the Jacobian. This is what we have discussed in this first slide of this continuous random variable. So, this fy y equals to this the absolute value of this Jacobian multiplied by this one, which is expressed in terms of this y. So, this multiplication, it can be proven that this multiplication with this Jacobian is nothing to ensure that this integrates to unity, which is the requirement of this PDF, you know. So, we can take some example, that is first and foremost, that example that we can take is that this for this from the normal distribution to this standard normal distribution. We know that this is known to us, earlier we explained, that is for the standard normal distribution, if we just take this one, this relationship, that is x minus mu by sigma, where mu is the mean and sigma is the standard deviation. So, this distribution of the y will become a standard normal distribution with mean 0 and standard deviation 1. Now, so this is one-to-one transformation, and if this is the one-to-one transformation, how it will happen, that whether using the same equation that we have used, it can be shown very easily that how it is transforming to this standard normal distribution. Similarly, for this log normal distribution, we know that y is equals to log x, if that y is equals to your that normal distribution, then x is the log normal distribution. So, we know that distributional form of this normal, then from that equation y equals to log x, this is also one-to-one transformation. So, whether using this one, whether we get that distribution of this log normal distribution, that we have already discussed. Now, we will see that whether from the normal distribution, whether that log normal distribution can be achieved or not. Similarly, for the others distributions also, we will see through different examples of this civil engineering problem in the next class. Thank you.